Hello and welcome to the solutions video for the Physics 20 practice test. So, here we go. In the last 10 years, astronomers have discovered thousands of exoplanets, which are planets that orbit another star. Astronomers observe one exoplanet orbiting with a period of 143 years around its star. And looking more closely, they find that the planet is a distance of 4.1 times 10 to the 12 meters from the star. So here we're going to calculate the mass of the star. We did the algebra in class. It is not on the formula sheet per se. We have mv squared over r is going to equal gmm over r squared, where the mass of the planet cancels and we're left with the mass of the star. And where v is 2 pi r over t, where that t is period, that'll be squared, gm over r squared. So then m is 4 pi squared r cubed over t squared, and we'll be dividing by g. So 4 times pi squared, our radius in this case is 4.1 times 10 to the 12, and that'll be cubed. Change the way I enter that in the calculator because I'm not sure if it's going to keep the 12 or the whole number. And I'm going to divide that by 6.67 times 10 to the negative 11. And our period squared, 4.52 times 10 to the 9. And with that, I'm getting 2.0 times 10 to the 30. So next, we've got a 600 kilogram toy on the end of a 1.2 meter string in a vertical circle. At the bottom, the toy has a speed of 9.46 meters per second. Well, if we have 0.6 kilos, or the magnitude of the acceleration won't have the kilos, it's just a v squared over r. So that's 9.46 squared divided by 1.2. So we're at 74 I'm getting 74.6. The answer key is keyed to 74.7. So this is probably rounding incorrectly internally. It will only affect some of the responses, but I didn't see any close but not quite right numbers. So it probably didn't affect you guys. So what is the speed of the toy at the top of the circle? So with this one, we've got the bottom. As it climbs to the top, we can actually do that with the conservation of energy that we did in Science 10. Or we can do that with just regular acceleration. So the speed at the top, it has gone up 2.4 meters. So the energy that it lost, right, if we go back, again, grade 10 conservation of energy, we have our kinetic energy, we have our gravitational potential energy. At the lowest point, that's the kinetic energy at the bottom, that's going to be the kinetic energy at the top plus the gravitational potential of going 2 radii up, because we've gone a full diameter when we're at the top. Canceling our m's and multiplying everything by 2, velocity at the top will be the square root of velocity at the bottom squared minus, and multiplying everything by 2, the 1/2s cancel, the 1/2s cancel. We have another 2 here, so it's going to be 4gr. So this is the square root of the velocity at the bottom, which was 9.46 meters per second squared, minus 4 times our 9.81 meters per second squared, times the radius of 1.2 meters. So we have the square root of 9.46 squared minus 4 times 9.81 times 1.2. And again, this rounds a little bit differently in 1 decimal place. So I suspect whoever built the question built it from the answers and didn't check the round this immediately button. This is why when I build them, I like to go back and force them to round immediately. Anyway, as the toy travels from the bottom of the circle to the top, its potential energy increases, so the kinetic energy must decrease if mechanical energy is conserved. Now, a satellite orbits Earth at an altitude of 410 kilometers above Earth's surface. That means the radius of the circle is 410 kilometers plus the radius of the Earth. So how long will it take to do a single orbit? So we have the distance above Earth's surface, we have the Earth's mass. So it's that same formula that we derived above. Once we derive it, we can just use it as is. So the period is again the square root of 4 pi squared r cubed over gm. So 4 pi squared. And confirming numbers with our formula sheet, radius of the Earth is 6.37. It says 10 to the 6 meters. And then we're adding 410 times 10 to the 3 meters, because that's in kilometers. And cube it. Divided by 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And the mass of the Earth, 5.97 times 10 to the 24 kilograms. So our period is 4 pi squared, 6.37 e to the 6 plus 410 e3 cubed, divided by 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. So this period is 5.56 times 10 to the 3 seconds. 5563. Now here, a 15-gram solution in a test tube is placed in a centrifuge that spins at a rate of 2.5 times 10 to the 2 hertz. 1 hertz is 1 over 1 second. If the radius of the motion is 12 centimeters, the centripetal force exerted on the solution. So centripetal force is mv squared over r, or so 4 pi squared r over t squared times m, but period is the reciprocal of the frequency, So here's our centripetal force. 4 pi squared. Our radius was 12 centimeters, so that's 0.12 meters. Our frequency is 2.50 times 10 to the 2 hertz. And our mass is 15 grams, so 0.015 kilograms, because everything goes to SI units. So 4 pi squared times 0.12, and that's going to be 250. Oh, and I forgot to square the frequency in the calculator. So almost messed that one up. But I'm getting the 4.44 times 10 to the 3, which is option D. So, assuming the orbit of the moon about the Earth is circular, which of the following is true? So the direction of the velocity is tangential to the orbital path of the moon. This is always true of circular motion. Direction of the acceleration is perpendicular. Yes, because that's pointing towards the center. Direction of the net force acting on the moon is outward. That would be false. And the magnitude of the velocity of the moon is constant. This would be true. The magnitude of the velocity is the speed. Velocity itself changes because the direction changes, but the magnitude of that velocity is constant. So, the satellites that transmit information used in GPS receivers orbit Earth at a distance of 26,570 kilometers from the planet's center. So how many hours will a GPS satellite take to orbit the Earth? So we can reuse our algebraic result from before. 4 pi squared r cubed over gm. So that's 4 pi squared. The orbital radius, they said, is 26,570, and it's kilometers. Over 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And the mass of the Earth, as it appears on the formula sheet, is 5.97 times 10 to the 24 kilograms. So this period is 4 pi squared 26570 cubed. And we divide that entire numerator by 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. So this period, so it's asking for hours, and I am getting 44,249.94687 seconds at 3,600 seconds per hour. When I run that through, checking for typos here because I'm getting a 12.3 and the answer key is keyed to a 12.0. So we're going to have to take a look at how things are rounded. Maybe they were using 5.98 or some other constants than we have on the formula sheet. So TESS, the Transiting Exoplanet Survey Satellite, was launched in April 2018. It's designed to search for exoplanets in a transit method in an area 400 times larger than that covered by the Kepler mission. So according to Kepler's second law, so TESS's speed will be fastest. The fastest point will be where it's closest to Earth. So fastest at point C, when it's closest to Earth. Now, Saturn orbits a distance of 9.58 AU from the Sun. And they're asking about the orbit in years. So yeah, this is the t squared equals r cubed. So this is going to be the square root of 9.58 cubed. So we can go through all the rigmarole with the exact numbers, and it'll round to the 29.6. Now, if an asteroid takes 3.50 times 10 to the 3 days to orbit our Sun, then its mean radius of orbit is. So we can take that 3.50 times 10 to the 3 days, divide it by 365.24. This is 9.582740116 years. We square the years, and then take the cube root of that answer, and that'll give us the radius in AU, which is 4.51. Now finally, a 300-gram ball is swinging in a vertical circle at the end of a 1.34 meter string. The speed of the ball at the bottom is 8.5 meters per second. We can do this like we did way back in this one, and do it with that conservation of energy. So the speed of the top is the square root of the speed of the bottom, which is 8.5 squared, minus 4 times 9.81, and our length, I think, was a 1.2 or 1.34 in this case. So that works out to a 4.43. So these are the solutions to the practice test.